With principal component analysis being popularized, scientists thought about using it to represent different types of inputs X. This was known as the Eigen-X paradigm, and researchers from Microsoft came up with the idea of representing faces compactly, meaning images of faces. This led to the idea of eigenfaces, which is something that we'll explore in the in-class session. The idea is pretty much as we've pointed out earlier. We're starting with an image that we can put as a vector, taking each row of the image and then concatenating it with the previous rows to form a long image vector, which could be just grayscale values. We're going to then take the singular decomposition of this large set of examples and truncate it to a specific point, where we use the top K components to represent the images lossily. We run PCA to get our K components as the singular values and their associated singular vectors, or eigenvectors. Then each face is going to be represented by a mean face plus coefficients that are being multiplied by the principal components, which are the vectors representing distinctive details of individual faces, arrayed from the most significant all the way to the least significant. Here we can see the reconstruction of a man's face on the left and a woman's face on the right. In both cases, when we have k equals 4, only 4 principal components, the faces look rather blurry and indistinct because we're only taking the first 4 components. But after taking an additional 46 components, you can see they start to shape up a little bit. Here with k equals 50, we have something that's distinctly a man's face, and here we have something that's distinctly a female's face, much closer to the input example that we have here. We'll close with a quick look at how SVD and PCA are related. PCA is basically an analysis technique that requires an eigendecomposition of the input. We truncate these to the top K in order for us to get an approximation that is optimal for the amount of storage that it requires. One way to go about doing this is using SVD. When we use SVD, we can get an exact replica of the input by using all n dimensions. When we do so, it's the same as PCA. We typically want to do dimensionality reduction, so we choose a K much smaller than n. And in SVD, this is nice because we don't need to compute the full covariance matrix under certain variants. And because SVD doesn't require a square matrix, this means that we typically use SVD all the time as a way of carrying out PCA.